Somewhere inside your body, right now, there is a particle that has been in continuous, uninterrupted motion since roughly 13.8 billion years ago. It has never stopped, it has never slowed down, it has never lost a single unit of energy to friction, decay, or time itself. That particle is the electron, and the fact that it behaves this way is not a poetic exaggeration. It is a measured, tested, peer-reviewed feature of physical reality that has forced some of the most rigorous scientists on Earth to admit they cannot fully explain why the universe allows it. This isn't a small, obscure detail buried in a textbook footnote. This is one of the strangest permission slips nature has ever handed out. Every other object you have ever touched, seen, or imagined loses energy eventually. Your car engine loses energy to heat. A spinning top loses energy to friction with the table and the air around it. Even planets, over long enough timescales, lose orbital energy to tidal drag. Entropy, the second law of thermodynamics, the whole architecture of physical law as we understand it, points in one direction, toward loss, toward decay, toward things running down. And yet the electron, one of the most fundamental building blocks of the atoms that make up you, this screen, the air in the room, appears to be exempt. To understand how strange this is, we need to be precise about what never running out of energy actually means here, because the answer is not what most people assume, and the real answer is far stranger than the simplified version taught in a first-year science class. Let's start with the basic setup, the kind of foundational fact you could find confirmed in any standard quantum mechanics textbook, because credibility matters before we get to the strange part. Every electron in the universe carries something physicists call spin. For decades, spin was described to the public using an analogy. Imagine the electron as a tiny ball spinning on its axis, the way the Earth spins once every 24 hours. That analogy is comforting because it's familiar. It's also, according to modern quantum theory, flatly wrong, and the way it's wrong is the doorway into everything interesting about this story. If the electron were actually a tiny spinning ball, as the old classical picture suggested, then to produce the amount of angular momentum and magnetic moment that experiments actually measure, the surface of that ball would need to be moving faster than the speed of light. Not close to the speed of light, faster than it. This was recognized as a serious problem as early as the 1920s, when physicists first tried to reconcile the experimental data on electron magnetism with a literal physical spinning sphere model. The numbers simply didn't work. A classical spinning charge, small enough to match the electron's known size constraints, would have to rotate at an impossible velocity to produce the magnetic effects being measured in labs. That contradiction told physicists something important. Whatever spin is, it is not rotation in the everyday sense. It's not a tiny planet turning on an axis. It's something else entirely, an intrinsic, built-in property of the particle itself, as fundamental and unchangeable as its charge or its mass. The electron doesn't spin the way a top spins. It simply has spin, permanently, as part of what it means to be an electron. This is where the story usually gets flattened into something simpler than it deserves. Most science content stops here and says, essentially, spin is just a quantum property, don't think about it too hard. But the actual physics goes much further, and the deeper you go, the more this looks less like a footnote and more like one of the great unresolved textures of reality. Here's the first real curiosity gap, the one that should already be nagging at you. If spin isn't literal rotation, then why does it behave exactly like angular momentum in every equation, in every conservation law, in every experimental measurement? Angular momentum is supposed to be a mechanical quantity. It's what a figure skater has when she pulls her arms in and spins faster. What a planet has as it orbits a star. It's tied to actual physical motion through space. And yet the electron spin obeys the same conservation laws, contributes to the same total angular momentum bookkeeping in physics, and shows up in real, measurable magnetic fields, all without the electron actually rotating in any classical sense. It's angular momentum without motion. It's a spinning top that isn't spinning. This single fact, properly understood, dismantles the intuitive picture most people carry around about what a particle is. We tend to imagine electrons as tiny marbles. But a marble that has angular momentum without physically turning is not a marble at all. It's something for which human intuition, built entirely from experience with baseballs and bicycle wheels and spinning coins, simply has no working analogy. Now here's where the story sharpens into the actual claim in the title, the one worth 13.8 billion years of attention. Because spin is intrinsic rather than mechanical, it cannot be spun up or slowed down the way ordinary rotation can. You cannot apply friction to it. There is no surface for air resistance to grip. There is no bearing to wear out. Spin is not a state the electron is temporarily in. It is a fixed, permanent quantum number, exactly like electric charge. An electron's charge doesn't fade over time. It doesn't leak away or decay. Spin is the same kind of quantity. It is baked into what makes an electron at all. And as long as an electron exists, it carries exactly the same fixed spin with exactly the same energy signature for as long as that electron has existed, which, if it happens to be one of the electrons that formed shortly after the early universe cooled enough for stable matter to exist, is a timescale stretching back roughly 13.8 billion years to near the beginning of measurable time itself. But intrinsic spin is only half of the puzzle. The other half, the part that makes this a genuine mystery rather than just a quirky definition, is the electron's overall stability as a particle. Because an electron that never runs out of energy isn't just about spin refusing to slow down. It's about the electron itself refusing to decay, refusing to break down into something else, refusing to release its mass energy the way almost every other subatomic particle in the known universe eventually does. This is where the investigative core of the mystery lives, and it deserves to be laid out carefully because it is backed by some of the most sensitive experiments ever built by human beings. Nearly every particle physicists have identified is unstable. A free neutron sitting outside an atomic nucleus decays into a proton, an electron, and an antineutrino in about 15 minutes on average. Muons, heavier cousins of the electron, decay in about 2 microseconds. Even protons, long assumed to be essentially eternal, are suspected by some extensions of particle theory to be capable of extremely rare decay, and experiments have spent decades hunting for any sign of it. Instability, in other words, is the default assumption for particles in physics. Stability is the exception that needs to be justified. So scientists ask the obvious, rigorous question: does the electron decay? Not does it seem stable based on casual observation, but does it decay in any way, at any rate, however small, that we can detect with sufficiently sensitive equipment? This question was taken seriously enough that a real, large-scale experiment was built specifically to test it. The Borexino experiment, housed deep underground at the Gran Sasso National Laboratory in Italy, shielded by more than a kilometer of solid rock specifically to block cosmic ray interference, was designed primarily to study neutrinos from the Sun. But its extraordinary sensitivity also made it one of the best tools ever built to search for extremely rare, exotic decay processes. Using data collected from this detector, the Borexino collaboration searched for a hypothetical decay in which an electron would break down into a neutrino and a photon, a process that would violate a fundamental conservation principle called charge conservation, but one worth testing directly rather than assuming away. The result, published by the collaboration, set a lower limit on the electron's lifetime, if it decays at all, of greater than 6.6 times 10 to the 28th power years. To put that number in human terms, the current age of the universe is about 13.8 billion years, or roughly 1.38 times 10 to the 10th power years. The experimental lower bound on the electron's lifetime is over a trillion times longer than the entire age of the universe has been. And that's just the floor. The actual value, if it decays at all, could be vastly higher still, or the electron might be perfectly, mathematically stable forever. This is the reversal the title promises, and it's worth sitting with directly. Physicists did not simply assume the electron never loses energy. They built an extraordinarily sensitive piece of equipment, buried it under a mountain specifically to filter out background noise, waited years for data, and tried to catch the electron in the act of breaking down. And it refused to break down. Not once, within a sensitivity threshold that dwarfs the age of the cosmos. So why is the electron protected this way? Why does nature seem to have built in a rule that keeps this one particle running indefinitely, while nearly everything else eventually gives out? The honest answer, the one grounded in the standard model of particle physics, is that the electron's stability isn't an accident or a mysterious act of cosmic favoritism. It's a direct consequence of conservation laws, and specifically of the fact that the electron is the lightest particle in the universe that carries electric charge. In particle physics, when an unstable particle decays, it must decay into lighter particles, and every decay must conserve certain quantities: energy, momentum, and crucially, electric charge. Charge cannot simply vanish. It can only be transferred, never created or destroyed, in any process observed so far. Since the electron is the lightest charged particle known to exist, there is nothing lighter for it to decay into while still carrying that same charge. It genuinely has nowhere to go. If it decayed, it would have to hand off its electric charge to some other particle, but there's no known particle lighter than the electron capable of carrying it. The electron is, in effect, stranded at the bottom of a mass ladder with a rule that says charge cannot be left behind. Structurally, physically, mathematically, it has no available path to decay. This is genuinely elegant physics, and it deserves to be presented with the credibility it has earned. But it does not fully close the curiosity gap, and viewers who stop here are being given only the comfortable half of the story. Because charge conservation explains why the electron cannot decay into something else. It does not explain why the electron's intrinsic spin, the very thing that generates its magnetic behavior, the property responsible for so much of chemistry, magnetism, and the structure of matter itself, behaves with such extraordinary, almost unnervingly precise consistency. And this is where the story pivots into genuinely cutting-edge, ongoing experimental physics, the part that separates a well-researched documentary from a shallow, recycled fact. For the past century, physicists have obsessively measured a number called the electron's magnetic moment, often expressed through something called the G-factor. In the simplest classical picture, a spinning charged object should have a G-factor of exactly 1. When Paul Dirac derived his famous relativistic equation for the electron in 1928, a landmark piece of theoretical work that successfully merged quantum mechanics with Einstein's special relativity, his equation predicted a G-factor of exactly 2, a striking non-classical result that matched experimental measurements astonishingly well for a first approximation, and instantly established Dirac's equation as one of the most important results in 20th century physics. But astonishingly well wasn't good enough for physicists who wanted true precision, and later, more refined experiments revealed the electron's G-factor wasn't exactly 2, it was very slightly more than 2, deviating by a tiny fraction. That tiny deviation, rather than being an embarrassing flaw, turned out to be one of the great triumphs of 20th century science, because it was explained by quantum electrodynamics, or QED, the theory developed by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, work that later earned them the Nobel Prize in Physics. QED accounts for the fact that an electron isn't simply sitting alone in empty space. It's constantly, briefly interacting with a churning quantum vacuum full of virtual particles winking in and out of existence. And each of those fleeting interactions nudges the electron's magnetic behavior by an infinitesimal amount. It's worth pausing on how strange this prediction looked when Dirac first published it, because the historical context makes the eventual confirmation even more remarkable. Dirac's equation didn't just predict an unusual G-factor, it also contained solutions for negative energy states that Dirac himself initially struggled to interpret physically. Rather than discarding these mathematically necessary but seemingly absurd solutions, Dirac took them seriously and proposed, controversially at the time, that they implied the existence of a previously unknown particle, one with the same mass as the electron but opposite electric charge. Many physicists were skeptical. It sounded like exactly the kind of speculative leap that gets quietly buried in physics history. Then, in 1932, physicist Carl Anderson, studying cosmic ray tracks in a cloud chamber, observed a particle that curved in a magnetic field exactly the way an electron would, except in the opposite direction, meaning it carried positive charge instead of negative. He had found the positron, the electron's antimatter twin, exactly as Dirac's equation had demanded years earlier. Anderson received the Nobel Prize in Physics in 1936 for the discovery. This matters here because it establishes something important about the credibility of the theoretical framework underlying everything we've discussed. The same equation that predicted the electron's non-classical spin and its G-factor of approximately 2 also correctly predicted an entirely new particle that nobody had previously detected. When a theory's strange side effects keep turning out to be real, physicists take its other strange side effects, like a particle that apparently never runs down, considerably more seriously. The precision of this prediction and its agreement with the experiment is almost impossible to overstate to a general audience, so let's make it concrete. In 2023, a team including physicist Xing Fan, working with Gerald Gabriels, a scientist who has spent much of his career pursuing ever more precise measurements of the electron, published a new measurement of the electron's magnetic moment using a device called the one-electron quantum cyclotron, essentially a trap that isolates a single electron and observes its behavior with extraordinary control. Their measurement pushed the precision of the electron's G-factor to roughly 1 part in a trillion, matching theoretical QED predictions to a level of agreement that is often described as the most precisely verified prediction in the history of science. If you scaled that precision up to a measurement of the distance between New York and Los Angeles, it would be accurate to within the width of a human hair. This is the actual weight of the claim in this video's title. It is not simply that the electron happens to keep spinning. It is that an isolated single electron, trapped and observed under laboratory conditions engineered with almost unbelievable care, displays a magnetic behavior, a direct signature of its unceasing intrinsic spin and its perpetual, undiminished interaction with the quantum vacuum, that matches theoretical prediction to 1 part in a trillion, with 0 detected loss, 0 detected decay, and 0 measured deviation over repeated experimental runs. Every test ever performed confirms the same picture. The electron simply does not run down. Now here's where the reframe deepens, because there's a subtlety in this story that most casual explanations skip entirely, and it's worth pulling into the light because it changes how you should think about energy at the subatomic scale altogether. When we say the electron never runs out of energy, we don't mean it in the everyday sense of a battery holding a charge until it's depleted. The electron spin isn't a reservoir of energy that could, in principle, be drained. It's closer to being a fixed identity marker, the same way a photon is always defined by moving at exactly the speed of light, or the way a proton always carries exactly the same electric charge. Physicists describe these as conserved quantum numbers, properties that are, as far as every experiment to date can tell, permanently and immutably part of what the particle is. Asking why an electron spin never depletes is, in a strange way, similar to asking why the number 7 never gets smaller. 7 isn't a container of some resource that could be used up, it's a fixed value. Spin and the associated angular momentum-like energy signature it carries appears to occupy that same category of fixed, immutable reality. Not a fuel tank, but a mathematical identity woven into the deepest structure of the particle. This is the point where the branded reality check on this channel needs to land, because it's the moment where popular science communication tends to quietly slip from precise language into misleading language, and it deserves to be corrected directly, on camera, for anyone paying close attention. It is technically imprecise and slightly misleading to say the electron never runs out of energy, as though it were somehow defying the laws of thermodynamics or generating free, usable power from nothing. The electron is not a perpetual motion machine in the sense that term is used to describe, and rightly dismiss, fraudulent energy-generating devices. It cannot be harnessed to power anything, because its spin energy is not extractable, transferable, or convertible into usable work in the way stored chemical or mechanical energy can be. What's actually happening is narrower, stranger, and in some ways more profound than a perpetual motion claim. The electron possesses a fixed intrinsic angular momentum and associated magnetic energy that is not subject to the same dissipative processes, friction, radiation loss, thermal decay, that govern every macroscopic rotating object we are familiar with. Because it isn't rotating through space at all. It is a quantum property, not a mechanical process. And it remains constant not because energy is being continuously and freely generated, but because there is no physical mechanism, no interaction pathway, by which that intrinsic property could be lost. Stability here isn't a victory over the laws of thermodynamics. It's an example of a particle existing in a category where those particular laws of dissipation simply don't apply, because there is no internal moving part to wear down in the first place. That distinction matters enormously because it reframes the entire mystery. This isn't a story about a loophole in physics. It's a story about the limits of the analogies we use to talk about physics, about how deeply human intuition, shaped entirely by a world of gears, bicycle wheels, spinning coins and worn-out batteries, fails to prepare us for objects that exist in a genuinely different category of behavior. The electron isn't cheating the rules. It's revealing that some of our rules, built from everyday macroscopic experience, were never built to describe it in the first place. There's a further layer to this that deepens the mystery instead of resolving it, and it involves a strange prediction that emerged directly from Dirac's original relativistic equation for the electron, a phenomenon called Zitterbewegung, a German term meaning roughly trembling motion, first identified by physicist Erwin Schrödinger in the late 1920s while analyzing the mathematical structure of Dirac's equation. Schrödinger found that the equations implied the electron should exhibit an extremely rapid oscillatory jittering motion, a kind of high-frequency trembling superimposed on its overall trajectory, arising from interference between positive and negative energy solutions embedded in the relativistic wave equation. This trembling motion, if it's physically real in the way the mathematics suggests, occurs at a staggeringly high frequency, far beyond anything directly observable with current single electron experiments in free space, though related effects have been observed in carefully engineered analog systems, using trapped ions and other quantum simulators designed specifically to mimic the mathematics of Zitterbewegung. Some physicists interpret this jittering as another hint that the electron's spin might be connected to an underlying, extremely rapid internal dynamic baked into the structure of relativistic quantum theory itself. Not classical spinning, but not nothing either. It remains one of the more actively discussed and only partially resolved textures of relativistic quantum mechanics. A reminder that even a century after Dirac's equation, the deepest nature of what spin actually is at the most fundamental level is still an open and active area of theoretical inquiry, not a settled fact tucked away in the back of a textbook. There's one more experimental thread worth pulling into this investigation, because it shows that physicists aren't simply resting on old confirmations, they are still actively hunting for any crack in the electron's apparent perfection. Beyond spin and magnetic moment, physicists have also searched for something called an electric dipole moment in the electron, essentially a test of whether the electron's charge is distributed with perfect spherical symmetry, or whether it's very slightly lopsided in a way that would show up as a tiny separation between positive and negative charge within the particle itself. A detectable electron-electric dipole moment would be a profound discovery, because the standard model of particle physics predicts it should be so vanishingly small as to be functionally unmeasurable, while several proposed extensions to the standard model, theories attempting to explain unresolved mysteries like the imbalance between matter and antimatter in the universe, predict it should be considerably larger and, in principle, detectable. The ACME collaboration, a group of physicists at Harvard and Yale working with cold molecules of hafnium fluoride to achieve extraordinarily sensitive measurements, published results setting an upper limit on the electron's electric dipole moment so small that it substantially ruled out a range of proposed new physics theories that had predicted a larger effect. In other words, physicists are not simply confirming that the electron behaves exactly as expected out of habit. They are actively trying to catch it deviating from perfect symmetry, using some of the most sensitive molecular physics experiments ever constructed. And so far, every attempt has come back empty. The electron keeps passing every test thrown at it, and each passed test narrows the space of new physics theories that would have required it to be even slightly imperfect. Step back now and look at what this actually means for you, personally, sitting wherever you are sitting, made of atoms that are in turn built from electrons, carrying this exact property. Every chemical bond holding your DNA together depends on electron behavior governed by this same intrinsic spin. The reason atoms don't collapse in on themselves, the reason the periodic table has structure at all, the reason 2 hydrogen atoms and 1 oxygen atom form water instead of some undifferentiated blob of matter, traces directly back to the Pauli exclusion principle, a rule discovered by physicist Wolfgang Pauli in 1925, stating that no 2 electrons in an atom can occupy the same quantum state simultaneously, a rule that exists precisely because of the spin property we've been describing. Every material object you have ever touched holds its shape, resists being pushed through the table it's sitting on, maintains its solidity because of electron spin. The stability of ordinary matter, the very fact that atoms take up space and don't simply pass through one another, is a direct macroscopic consequence of a property that traces all the way back to those same electrons that have been carrying identical, undiminished intrinsic spin since shortly after the Big Bang. This is the bridge worth sitting with before we close. The electron's refusal to run down isn't an isolated curiosity confined to a physics laboratory. It's one of the load-bearing pillars underneath the existence of stable matter itself. If electrons decayed, if their spin dissipated over cosmic timescales the way a spinning top eventually stops on a table, the atoms in your body, the ground beneath your feet, the sun overhead, none of it would hold together in anything resembling its current form. The 3.8 billion year persistence of electron spin isn't a party trick of subatomic physics. It is one of the quiet, unglamorous conditions that had to be true for a universe like this one, with stars, chemistry, planets, and eventually observers capable of wondering about any of it, to exist at all. And that is where the genuine evidence-based mystery still sits, unresolved, at the frontier of modern physics. We know, with extraordinary experimental precision, that the electron's spin does not decay, that its magnetic behavior matches theoretical prediction to 1 part in a trillion, and that its overall stability as a particle is protected by the mathematics of charge conservation, verified experimentally to a lifetime bound exceeding 6 × 10⁻28 years. We know the trembling motion implied by Dirac's own equation remains only partially understood and is still an active area of investigation using quantum simulators and precision trap experiments. What we do not have, and this is the honest, evidence-first answer this channel exists to give you, rather than pretending the case is fully closed, is a complete first principles explanation for why the universe's mathematical architecture happens to produce a particle with exactly these protective properties in the first place. Physicists can tell you, with confidence backed by some of the most precise measurements ever performed, that the electron cannot decay and its spin cannot dissipate. What remains genuinely open, debated in serious theoretical physics literature to this day, is why the deep structure of reality is built in a way that allows, or perhaps requires, a particle like this to exist at all. So the next time someone tells you that nothing lasts forever, that everything eventually runs down, that entropy always wins in the end, you'll know that somewhere inside every atom in their body, and yours, there is a particle that has been quietly defying that intuition for 13.8 billion years, not through some hidden trick or violation of physical law, but by existing in a category of reality our everyday experience never prepared us to understand. The mystery isn't that the electron cheats the rules of physics. The mystery is that the rules of physics, understood clearly enough, were always stranger than the intuitive picture we grew up with. And the electron has been running proof of that fact since very close to the beginning of time itself. If this kind of evidence-based reframing of the physical world is the kind of curiosity you want more of, this channel exists specifically for that, one case file at a time.